Okay, so the lesson that we were covering today is 3.9, which is inverse functions. And inverse functions has two parts to it. One, we have some inverse derivatives that we're gonna look at, and that is within your Bible. So there are the functions that I'm talking about. They're down below towards the bottom of that differentiation rules. Those derivatives are there. So those are some things that we're going to work with. We now have the derivative for arcsine, arccosine, arctangent, arccosecant, arcsecant, and arccotangent. But the other side of this is just working with what we know of inverses and seeing if we can go ahead and apply that knowledge to finding derivatives, because this part is pretty easy. We can go ahead and use this to just apply with our other rules, although they can be kind of tricky in the application. I'll do a few examples. But then the other side of that is some other stuff that's attached to this, the idea of inverses. So to do that, I want to review some inverse stuff for you with the stuff that you've had from previous classes. I'm trying to get my pencil. So inverse knowledge. From a previous class is that the inverse is probably the most obvious one, is that it's a reflection over y equals x. That's the graphic definition of it. And that's what's happening. You're kind of rotating that graph so it's reflected over y equals x. But what you might also not realize, or what you've done before, is when you switch the y and the x to find it algebraically. So the trick, so to speak, in a previous class, if you had like y equals plus 5 and you wanted to switch it to an inverse, you'd go x equals 3y plus 5, and then you'd solve for y. So minus 5 divide by 3. So that would be 1/3 x minus 5/3 equals y, and then you'd have the inverse of this is this guy. So that's the idea that an xy within f of x can transfer over so that it's yx within f negative 1 of x. So that's another piece of inverses. So one thing you might know about inverses is that it's a reflection over y equals x. The other piece you might know about inverses is that the xy in f is the yx in the f to the negative 1. Okay? So this is all stuff that you should know about inverses. However, some of it you may need this review. But with that x, y, y, x transition, that does indicate that sometimes the domain for one function can turn to the range of the inverse, and the range for one function can turn into the domain for the inverse. Now that is not always, so be careful. That only works for a one-to-one graphable type of a situation. So be careful with that, because we're going to do an example where that's not the case. What is always the case is that the composite function of the inverse and the original function should always equal x, and that does not matter if you do the composite of the inverse on the outside or on the inside. Okay? We have f of x equals the square root of x to the third plus 8. I would like you to determine domain and range for this. I would like you to find f to the negative 1 and the domain and range for f to the negative 1. And then go ahead and graph this on your graphing calculator just to get a picture, and then try to see if you can sketch out and imagine the sketch of this within your graphing calculator, or possibly graph this f to the negative 1 within your graphing calculator and visually inspect if they're inverses. Pause here if you'd like some time to work. Okay, so the domain of f is that x can basically, since it has a square root, that piece can't be negative. So x to the third plus 8 must be greater than or equal to 0. And I know a cubic basically looks like this, and it's a positive cubic. So I need to find where the 0 is, and then everything less than that, it can't be negative, because you can't find the square root of a negative number. And so the cubed root, x to the third equals negative 8, and I can find the cube root of that so that x is equal to negative 2. And so that means everything here, this negative 2 and onward, is going to be fine, and everything below negative 2 is no bueno. So that means that I can start at negative 2 because negative 2 will make it 0. Anything smaller than negative 2 will make that radical negative. And I can go all the way up to infinity. So that's my domain. And then the range, likewise, can go start at 0 and can go all the way up to infinity. But it can't be anything negative. So then the f of negative 1, to find that, you can pull that sneaky trick where you make x equal to the square root of y cubed plus 8. So x squared minus 8 equals y cubed. And then the cubed root of x squared minus 8 equals y. So that is the inverse. And so now I would encourage you to go ahead, if you haven't yet, go ahead and graph this guy against this guy to see if they look like inverses. Now, unlike the last one with the domain, I can have a negative underneath the radical in this case. And moreover, when I put a negative in the x, it's not going to stay negative because I'm going to square it out, which means it goes positive. So my domain here is negative infinity to positive infinity. My range, however, bottoms out at 0. Or excuse me, the range, this piece inside the radical, the x squared, will bottom out at 0. Because if I go below 0, it will just match what happened with the positive. This is an even function. It's this parabola underneath. So if you're just looking at that underside, this will never get anything lower than what happens when x is 0, which is negative 8. And negative 8 cubed roots to be negative 2. So this bottoms out at negative 2 and then goes all the way up to infinity. Okay, so I will tell you that I have posted 2 graphing exercises. That I didn't want to put in here to discuss, partially because it's really hard for me to sketch an inverse on this sheet. So I posted them on Canvas for you to work on in class. You can pause the video here and go ahead and work on that, and then I will actually stop this video at this point and start the next one. So stop here, work on those on Canvas, and then we'll be ready to move on to the calculus portion and not so much the review.